name is Jeremy Munsell, and I'm a graduate teaching assistant at Purdue University in the Department of Physics and Astronomy. I've been involved in education my entire life, first as a student, and then later as a teacher and a researcher in physics education research. This is the video that I made to show you my teaching in action. All right, let's get started. So first thing we're going to do is we're going to do a simple thought experiment. Okay? So imagine I have some ice that's really, really slippery, so much so, in fact, I can call it frictionless. Okay? And let's say that I have a block on this frictionless ice, and now let's say that I start experimenting with it, right? I push it, I pull it, whatever. And some things that I observe is the harder I push on the block, I'm talking about just for a short time getting it going, I notice that the harder I push on the block, the more it seems to speed up, right? So if I give it a light push, it goes with some small speed. If I give it a big push, it speeds up and travels with a much larger speed. Okay? Does everybody agree with that? Okay? So next thing, a heavier block is harder to push, right? So if I have a really light block, I can really get it moving, okay? But if it's a really heavy block, I can push up really hard and barely get it moving. Does that seem reasonable to everybody? Yeah? Okay. My third observation is if I push the block to the right, it moves to the right. And if I push the block to the left, it moves to the left. Seem reasonable? Okay. And another thing I notice is, since it's frictionless ice, right, I'm an idiot, I'm walking out on the ice, and I try to push the block, I notice that when I push it, it moves in the direction I push it, but I move opposite to the direction I push it. So if I push it this way, I slide back this way. Does that seem reasonable? Does that seem consistent with your prior experience? Okay, so those are the observations we're going to start with, okay? And we're going to try to explain those in terms of some law that deals with forces. Oh, one more thing that I should notice, right? So let's say that I'm pushing the block for a while, and it speeds up all while I'm pushing it, but once I stop, its speed stops changing. Okay, that one might seem a little more subtle, but I'm going to demonstrate later with this that that's also true. Okay, so those are our 5 observations that we're going to start with. Now, before we go on, one thing we have to talk about, kind of a subtle thing about motion, right? We want to differentiate between velocity and acceleration. Now, acceleration is defined to be the change in velocity divided by the amount of time that it took to make that change in velocity. So that's the definition of acceleration. Okay? So some things we should notice. Velocity is not the same as speed, right? Speed is a scalar, it's a number with some units. Tells you how fast you're going, but velocity is a vector. So it also cares about the direction. So to that end, velocity can change if the speed changes, that is, the magnitude of velocity changes. Also, velocity can change if the direction changes. So if the direction of motion changes, then that's also technically an acceleration. Okay? We're going to deal with acceleration due to changing direction in chapter 4. Okay? But for these first chapters here, we're going to be focusing on this one, which is acceleration due to a change in speed. Actually, I guess that's not true. So you can, in these first chapters, the change in direction is going to be abrupt. It's going to be like you're going to actually reverse direction. So I'm going to the right, then some force acts, and then I go to the left. Okay? But in chapter 4, we're going to be considering circular motion. So I guess I should have been a little more careful with that. All right, so with this idea of acceleration, we can go on and kind of explain some of those observations that we made initially. Okay? So if we return back to those observations, right, the harder I push on the block for a short time, the more it seems to speed up. Right? Well, another way I can say that is the force that I apply is proportional to the acceleration. So the higher the force is in magnitude, the higher the resulting acceleration will be in magnitude. Does everybody understand that? Does anybody have any questions about that? Okay, so what's going to happen, just like with a rocket, right? As the propellant leaves, it's going to, by Newton's third law, produce a force on me. Okay? And that force is going to be directed this way. So what do you guys expect is going to happen? It's going to accelerate that way, right? So if this doesn't kill me, then we'll talk about it after. All right. Let's see. All right, here we go. So this one is pretty similar to one that's on your homework. A green car is moving at 22 meters per second at the same time that a red car is moving at 31 meters per second. The red car starts 750 meters behind the green car. It wants to know how long does it take for the red car to catch up with the green car. Okay? So first thing I'm going to do, luckily I have red and green markers, so I'm going to go ahead and draw a picture. So I have the red car that's initially moving with velocity v red. And I have a green car which is initially moving with velocity v green. Okay? So the next thing I need to do, since I've drawn the picture, I need to decide on the system of coordinates. Okay? So what I'm going to do is I'm going to say that to the right is the positive x direction. So that velocities pointing to the right are positive, and positions to the right of some origin that I haven't picked yet are going to be positive. Now, for this problem, you can do it any of like several different ways, but probably the most straightforward and easiest with respect to calculation is to pick my origin, that is x equal to 0, at the position, the initial position of the red car. Okay? So I'm going to call this position, which is the same as the initial position of the red car, I'm going to call that x equals 0. Right? And since the red car is a distance of 750 meters behind the green car, then what is the initial position of the green car? 750, right? It's positive because it's to the right. And that's the consequence of saying to the right is positive. Okay, so that's going to be 750 meters, right? But I don't like to use numbers right away. I like to do algebra and then plug numbers in at the end. So I'll just call this some d, some distance d. Okay, so now I'm going to go to my list of kinematics equations. And what I'm going to do, I have information about velocities, okay? I have information about positions, and I want to know at the end what the time is, okay? Well, let's think also, right, if I look here, I'm just given these two speeds, right? And actually it's one speed for each object. So what can I conclude about the acceleration of each object? It's got to be 0, right? Because this problem statement implies that each car is moving at a constant speed throughout the problem, right? Otherwise, they would have to give me another speed, right? If it's changing, I need to know the speed it's changing to, or they would have to give me the acceleration, right? So they don't explicitly say the acceleration is 0, but I can reasonably conclude that from this problem statement. Sounds good. Okay. So we have charge Q1 has some charge 5Q, like we talked about before. Okay? And we have charge Q2, which has charge Q. Okay? And they are some distance 207 meters apart.